start with the solids and structure section, which is prepared and presented by Astrid Pechsteins and Michael Neunteufel. So Astrid, I think, will start. Astrid has done her PhD in 2008, 9, something like this. So she was NGSolve user number 1, 2, 3 in this room, one of the first. She brought in a lot of new stuff, in particular elasticity. This mixed methods in elasticity, now known as TD and S methods. Started with, let's see, so displacement in H curl and stresses in H diff, fancy function space, matrix valued function space, which triggered a lot of development, ongoing development, and with particular use in mechanics. Astrid had done her PhD in numerical analysis. So if you look into the work, it's heavy numerical analysis and advanced function spaces. But then she switched later to the Department of Mechanical Engineering. And luckily, she is using this method successfully in engineering applications, in particular with plates and shells and structures and coupled field problems. And she will present some of her developments there, which can be used for communicating this method. So thank you very much, Astrid, for sharing your work on this, and we're looking forward to your talk.
Yeah, so thank you for the introduction. Okay, I hope it works. So yeah, thank you for the introduction. So I'm going to present you some introduction and more advanced NGSolve models in solid mechanics, also structural mechanics together with Michael. I'm doing a lot of teaching with NGSolve, getting my students to install it every year. Every year it works better. So this year it was like 5 minutes, do pip install NGSolve, and they all said, okay, it works. That was really great. Thank you, Joachim. Thank you, crew. We do NGSolve mainly mechanics, also in coupled problems. So that's where we will come to in the end of our talks, Michael and me, to coupled problems, elasticity and something, fluid mechanics or electrical electrostatics. Well, yeah. But first, the introduction. So the first part of the talk is from the point of view of mathematics simple. It's just the implementation in NGSolve that is interesting to all of us, I think. So what we consider is, so there I have some fancy geometry, well, a little bit fancy, where you see how to model in Open Cascade. I think you discussed this yesterday. How to
repeat it.
Okay.
Only part was here yesterday. So
okay. Open Cascade geometry generation is not what I can do best because I learned NGSolve when it wasn't there. But I learned a lot during the last week. And so the nice thing is you can do things where you always think that has to be simple to do, which was not simple when using like the old geometry formats you maybe know. Like here we have a block. You see a block and you drill 3 holes, circular holes, cylindrical. And then you say like, oh, the edges are too sharp and we want to round them off. Like, so drilling the cylindrical holes is just subtracting cylinders from the box with those 5 lines of code. But then you want to like not have the sharp edges. And it's 1 line of code, essentially 1 Open Cascade command to get these, I don't know what it's called, chamfered edges. Yeah. And then we need to we want to propose to have some boundary conditions on this part. So what we want is, do I have a laser pointer? I think. Here we want to fix it, and here you want to have some force acting, and in between there are no surface forces, there is no volume load, so it's a very simple example. But what we definitely need is somehow we need to mark this part of the boundary and also that one. And that's what you can do in Open Cascade with simply addressing all forces with minimum, maximum, x, y, z component, all forces, all faces with minimal distance to some given point. And then if you have done so, you can just click on the face, and very nicely it tells you, okay, I did the correct thing because this face is now called force, just as specified here above. And that one should be called fix, and all the others are something like outer, which was specified somewhere above. So all the others we don't need to address. Then we generate the mesh, and NGSolve will do so using tetrahedral elements in general. Okay, and that's the mesh, and now we go to the elasticity. Linear elasticity first, then we go to nonlinear elasticity, and then we go to advanced or mixed elasticity methods, and then to structural mechanics, shells, plates, beams, whatever. So that's the same geometry put here in this notebook again. Short recollection of the standard linear elasticity problem. How many of you are associated with linear elasticity at some point? That's not a lot. Okay, in elasticity, we are usually concerned with finding displacement field. Displacement field here, vector valued u. And we do so by, in this linear elasticity example, we say we have the linear strain tensor, which somehow tells us how much the body is deformed. We have the stress tensor, which tells us which forces are acting locally in each point, in each direction in the body. Then we have an equilibrium equation, which tells us that the divergence of the stress tensor, which is essentially locally the forces acting in the body, equal given body forces, F, that would be like gravity, something acting within the volume, a volume density. We have traction boundary conditions here. That would be on the force boundary part, where we say the stress vector, sigma dot n, n is the outer surface normal, equals some given load per area. And we have some displacement boundary conditions, like the body is clamped on the left-hand side. There is no displacement happening there. And then you take these equations, plug them one into the other, and do some multiplication with the test function and integration by parts, and you push in the boundary conditions, and you get the very variational formulation, which is put here. So that's kind of the apart from the Laplace formulation, probably the most basic one of variational formulations you treat in a typical master studies of technical mathematics. A linear variational equation. It works in H1 space, so you need first derivatives of the displacement vector. It's vector valued, and there is a right-hand side which is like all continuous and bounded and whatever you need from your right-hand side, and the left-hand side is somewhat if all the material constants are above, away from zero and nice and not infinity, then you have some coercive elliptic bilinear form and everything is correct and you can do error analysis and whatnot. We want to do now an implementation in NGSolve for this bilinear form, for this problem. So we have some kind of values for the material, Young's modulus and Poisson ratio, or rather we use the Lamé constants, which are equivalent. And then what do we need? We need the stress tensor as a function of strain. In linear elasticity, we assume that the stress depends linearly on the strain tensor. This linear relationship is put here as a Python function. Then we need, as you know, in NGSolve, we have the finite element mesh. Then we define finite element spaces. And for the finite element space, we define grid functions, which is like the solution vector. We define a bilinear form, which is essentially the system matrix. And we define a linear form, which is essentially the right-hand side of the problem. So here we have vector-valued H1 elements, which is the finite element space. We put here Dirichlet boundary condition, where we have the fixed part of the boundary. And then we get a grid function, which contains the solution vector in some sense. So the G of U is the grid function. Behind it is the solution vector, all the unknowns, and the information how to get the degrees of freedom of this solution vector into a field which you can plot. Then we do the bilinear form, which is the system matrix. We want the right-hand side, left-hand side of our variational equation. This is this one line. We define trial and test function u and v, as you usually do in mathematics, and then put that formula, stress times strain, into the bilinear form, simply putting there an inner product and multiplying in the end somewhere by dx, which tells NGSolve that it's a volume integral, as we had here. Preconditioner I don't want to talk about now, because I think we will hear much more about preconditioners in later sessions. And then we simply say, bilinear form, assemble yourself. We have the system matrix, we have the solution vector, we need the right-hand side vector, which is the linear form in the language of mathematics. That would be this cell down here. So we have a force which we want to have acting on the right-hand boundary of the body in a positive x direction, so that would be pulling. And then we tell NGSolve, okay, generate me a linear form. That will be my right-hand side vector. Put there the force times the test function v, and integrate ds, integrate on the surface, which is called force. That would be the right-hand side surface. And then we say, assemble yourself, and it's done. Well, and then the rest, now we have a matrix, a vector, and another vector. We do a solution procedure with preconditioned CG iteration and get a solution. So there we are done with the actual computation. The rest is some post-processing. Probably you want to visualize not only the displacement function, but also stresses, because you may be interested in the maximum stress arising in this kind of computation, because you want to do some analysis if it will hold or not. So what we put here is another grid function where we want to store the stress state in some matrix valued grid function, because the stress is a tensor 3 by 3. And then we simply say, interpolate yourself to the function stress, the Python function stress we have given above. Well, and then the visualization works nice. Somewhere here you can do some deformation scaling, I think. Yeah. So I'm not an expert with this web GUI. But it works like that. Okay. Okay, so that was the point of view of mathematics. Now we come to mechanics. I have almost used half of my time. In mechanics, we don't do bilinear forms and linear forms. And whenever I tell my students about bilinear forms, they get really, well, that was what we learned in the numerics and optimization course, and we didn't like it. But we talk about the principle of virtual works. Is anybody here who knows about the principle of virtual works? Yeah. it's essentially, so it's the same. In the end, it's the same. It's just the language that changes. And why do I present this here? It's because in NGSolve, this language is quite naturally included. All we have to do to get to the principle of virtual work instead of the variational formulation from above is we call our test function not v, but delta u, and say it's the variation of u. The variation of u has to be kinematically admissible, which means no gaps opening up in that body. The Dirichlet boundary, so the clamp boundary condition, has to be respected. That's essentially, we are in the finite element space we had above. So we say delta u is the test function for the finite element space. And then the principle of virtual work, as you know, is the virtual work of internal forces plus or minus, so the sign is depending on which school you're coming from. The virtual work of external forces equals 0. And what is the virtual work? And here I chose a formulation which we can directly take to nonlinear problems, because most of the time in elasticity you have nonlinear problems, not linear ones. The virtual work of internal forces is defined as the variation of the free energy you have within your body. For the free energy, we may have an expression like this here. So that's the expression valid for the linear elasticity case of Hooke's law. We have an energy that's a convex function of the strain epsilon. We can put its variation here, derived by the strain multiplied by the virtual strain, where the virtual strain is simply the linearization of the strain in direction of the virtual displacement. And then, so the virtual work of internal forces is the variation of energy by our virtual displacement. And for the virtual work of external forces, we have some expression given by the forces acting on the system. So usually it's force acting times virtual displacement integrated over whatever domain is of interest. And then we put the same problem we have above within a few lines. So now we say u and delta u are our trial and test function. Delta u the virtual displacement, u the displacement. We put some Python function here as a psi of u, where I define the strain tensor independence of the displacement, and then I return this quadratic function, the free energy function. And then I tell the bilinear form. Bilinear form is not really a bilinear form anymore. I rather, when I talk to my students, I tell them it's a container and you put everything in it you want there. So we put in the variation of the energy we had before. And we put in the virtual work of external forces in the second line here. And that's all that is there to the linear elasticity problem. So now we are finished. Now we still need the degree of freedom vector we have. So this is this G of u. We need a stiffness matrix and a load vector, right-hand side vector. So what do? We say bilinear form container A, which is not linear anymore. It's affine linear in this case, but not linear. Assemble your linearization around the vector, which is at this time 0, but it's of no effect if it's an affine linear function. And then we define the residual of our equation, where we tell the bilinear form container, so our variational formulation, to apply itself to some current state of solution vector. Well, and then we solve the linear problem in whichever way we like. If direct solver or preconditioning it's not so much relevant. And then in the end, of course, we get the same solution. It's an equivalent formulation of the problem. Okay. Questions so far? Then we go to nonlinear elasticity. And here we see that it's essentially exactly the same. There's not much we have to change if we go from linear to nonlinear elasticity regarding the NGSolve framework. So what do we need just to fix the notations? In nonlinear elasticity, we don't have the linear strain tensor, of course, but we usually have F for the deformation gradient, We have C for the right Cauchy-Green tensor, F transpose F. We have the green strain tensor, 1/2 C minus identity. And we might need the Jacobi determinant J, which tells us the size of change of volume in this body. Then we have a number of different stress tensors in elasticity. The Cauchy stress tensor, which is relevant if you want to have equilibrium in deformed configuration, so in the state you are in now. The first Euler-Kirchhoff stress tensor, which is in equilibrium with respect to the reference configuration, so with respect to the stress-free configuration, which is in which you have your finite element mesh in which you do the computations. That one is not symmetric. The Cauchy stress tensor is symmetric. And we have the second Euler-Kirchhoff stress tensor, which this relation, of course, is wrong. So you should have here an S for the second Euler-Kirchhoff tensor. So this is the one, the second Euler-Kirchhoff tensor is the one for which you usually have the material law. And then all we have to change in our code is we have now, again, an elastic energy density, maybe hyperelastic or whatever you call it. And it depends not on the linear strain tensor, but on the right Cauchy-Green tensor, or you can also define it in terms of the deformation gradient. The simplest one, simple extension from linear elasticity to the nonlinear case would be the Savannah-Kirchhoff material model, where instead of the linearized strain tensor, we just put here the nonlinear strain tensor E. The principle of virtual work is still the same. That did not change. The variation of the energy equals the work of external forces. That's true in D4, in linear and in nonlinear elasticity. There is no need or no reason to change the principle of virtual work. Well, and that means the implementation of the nonlinear elasticity problem is exactly of the same, it's not more difficult than implementing the linear elasticity case. So we use the virtual work formulation. We have now a different representation of the free energy function where we have the nonlinear equations. And here you could put in whatever nonlinear free energy function you want. It's not necessary to be a Savannah-Kirchhoff material. You can put, I don't know, Neohook, Octon. No, Octon is difficult. Octon is not good. Mooney-Rivlin, Yeo. Octon is not good because you have eigenvalues, and differentiating by eigenvalues is not so great. Not a good idea. And then we have the bilinear form. We put there the deformation, the variation of the free energy. We put there the virtual work of external forces. And then we don't do a linear solve, but we do a Newton solver. So it's even less to write for me, because all this defining the residual and assembling the linearized stiffness matrices is done within the Newton solver. And then we do some iterations. That was a small strain example before. So the Newton solver converges like on the first or second step, depending on how accurate you want it to be. And then we can do the visualization. So now the question is, we want to do the visualization. The deformation is simple to visualize because that's the same as before. But we want to visualize the stresses. How do we do that? First, we need to know how the stresses are defined. We didn't need them here. There was no explicit definition of the stress tensor. But we know that the stress, whether you want the first or second Euler-Kirchhoff stress, is given as a derivative of your potential by the deformation quantity you need, either deformation gradient or the strain tensor, depending on which kind of stress you want to visualize. And this is easy to visualize in NGSolve, because here we can just say, like here I visualized the first Euler-Kirchhoff tensor, P equals the derivative, that's this diff function here, the derivative of the potential by the deformation gradient. And it just works out. And you can draw it and see here like the XX component, so the longitudinal stress component in this body. Well, and then, of course, if you apply larger force, you will do some load stepping. That was done here. The definitions are the same. What we add is a parameter that allows us to do load stepping, that allows us to increase the load in whatever step size you want. So we have a parameter inside here. And then it's one more iteration superimposed. And you see here the evolution of the X displacement component. Okay, and time is running out. So the next...
You mentioned the problem with the oxygen materials, since you cannot differentiate with respect to the eigenvalue.
Yeah. Is it? What? Can you do that now?
Okay,
so last time
it's a missing feature. Let's see what we can do.
So I'm not sure if it's possible to differentiate by if it's a differentiable process. I'm not sure about that.
If it's not differentiable, then we cannot do it.
Yeah, so I'm not sure if it's possible on the really to differentiate a tensor by its eigenvalues. So I'm not sure. So there is another problem. I will go over that very quickly. That was just like to see how you can do some more advanced, some problem where the solution is not so very easy. So that's like a balloon or something that is loaded from the inside by pressure, hydrostatic pressure from the inside. So there is a hole here, it's clamped. And if you put enough pressure, you will this part up here will like snap through to some from the concave to a convex position. So there is some critical point during the loading. So we do the computations in 2D because it's much cheaper on an axisymmetric mesh. What do we have to keep in mind? So one thing is hydrostatic pressure is always acting in direction of the surface normal, but not the surface normal you see here in undeformed configuration, but the surface normal which you have at the actual state, at your deformed state. So we need a transformation from our surface normal in deformed configuration to the actual configuration. And you can do this formula in NGSolve, you see it below. Also, you need maybe to scale the volume integrals from reference to deformed configurations. Okay, and then there is another issue in this case. We want to go through this snap-through point as smoothly as possible. And if you go through snap-through, you will have, first you increase the pressure up to the critical point, and then the pressure will go down. You have the snap-through, and then it will grow again from a lower level. So increasing the pressure all the time is not possible physically, because it will fall at snap-through. That's why we add the pressure as an additional unknown. That's also something you can do in NGSolve easily. Add one additional line to your system, one Lagrange multiplier, that's the internal pressure. And then control that via its dual, which would be something like the mean normal displacement in deformed configuration. We have now a mixed finite element space. Displacement pressure elements because it's an incompressible material. And this pressure is the internal surface pressure, which is our Lagrangian multiplier. And then you can do all the computations for, I think you have to read it yourself to go for the axisymmetric case. The load stepping is the same as above. So that's not very complicated. We just do the Newton iteration, this times Newton with line search, because otherwise it won't converge at the snap-through point.
So the built-in Newton was not enough.
No, it works for all the configurations, but the snap through. There you don't get convergence. And then, yeah, here you see how it works out. Oops, and there it went outside. Yeah, so you see here the mean normal displacement on this axis, pressure here. We go up with the pressure. Up to here it would work if we increased pressure just by prescribing it. Here it would break down at this point. For our case, the pressure, we lose some pressure. There is some second buckling mode evolving in this convex-concave structure. And then we have the snap through, and then it's stable again. Okay. So very short now, we come to mixed elements. Mixed elements, so this is what I did in my thesis like almost, 20 years ago. There was this idea of Joachim. He told me there is locking in linear elasticity or in elasticity as a whole, but we were treating linear elasticity then. There is locking if you have flat, thin elements. And in mathematics, you always learn locking is due to Korn's inequality. In the mechanics department, I learned locking described as something much more visible. Just imagine a finite element mesh defined by two elements which are rather flat. We prescribe bending, so that the deflection here is prescribed, how far it has to go down. And then do the deformation using just two linear elements, and what we get is a lot of shear strain in here. So here we plot the shear strain component, which tells you just how much the angles change locally within the body. And that's a lot. So the shear strain in here is something like 5 to 6% positive and negative direction. The force we need to get to this deformation is above 100 Newton per square millimeter. And then we do the same computation again using higher order elements, which is very simple in NGSolve, just put 5 instead of 1. Do the same computation, and we see something that looks much more realistic because it's bending now and not just shearing. And we see the shear strain, the same strain component. Shear strain component is now below 1%. Even rather like 0.1%, so much lower. The force we need to get to this configuration is like 11 Newton per square millimeter, so 1/10 of the value we estimated before. And now the question is, what can we do about that? And the idea is, in a nutshell, what we do is we relax a little. This is very stiff, so we relax at this edge here. Essentially, we give the deformation the capability to have some gap opening up here, like to have some of the shear in this gap. So we have a normal gap in the displacement, and then we add, because we have a normal gap, we need something to control that gap. We add the normal stress as a Lagrangian multiplier on this interface. So that's the idea here. We have a normal gap in the displacement. We add a normal stress at the interface. A normal gap means the displacement is tangentially continuous. And that's what NGSolve has from its beginning on, I think. Tangential continuous elements are Nedelec elements, which are well known as in Maxwell formulations for the electric field. So those were already there. What we need to add is something that has a normal stress as a degree of freedom. And there we developed stress elements, tensor-valued elements, with a continuous normal component. So sigma n dot sigma dot n as a continuous value. And then we do a little bit, so we transform the system the principle of virtual work to a Reisner type formulation where we have stresses and displacements as unknown. We do a Legendre transform, and then we do the computation. And then when we do, again, for linear, so for lowest order elements, the degrees of freedom are linear, the shape functions are not. That's why it looks so good. We get something where, I don't know, so I don't see the gap in here, but you should see it somehow. I don't know. It has to be very small, otherwise the solution would be wrong, so probably because of that. And the strains are, again, very small. When we compare the force, we see 11.45. That's even below the force we had before. So the forces and stresses are underestimated in this mixed method. Yeah, and so that's the formulation we use in the end. A Hellinger-Reisner type formulation where we do a Legendre transformation to get the stresses in there. And then we need to think about work pairs like that. Stress times strain. The strain is now not really existing because we have gaps in the displacement. A gap leads to an infinite amount of strain. But on the other hand, the stress is continuous there. And you can show somewhere below. Didn't I put, okay, here. You can show that you can replace this work integral, stress times strain, by something, stress times strain on each element, and the normal stresses that are degrees of freedom acting on the normal gap that is opening up as a Lagrangian multiplier. That's all you have to do. Replace the work integral by this expression, or equivalently, after doing some integration by parts, by something like that, depending on which differential operators you like best. And then that's the formulation put in NGSolve. And now I think I should hand over to Michael to have some structural mechanics.
Before you give it to him, give it to me. Thank you, Astrid. I think it's really cool how you teach these advanced measures to your engineering students. That's very intuitive. So the next second part of this block is given by Michael Neunteufel. Michael has done his PhD finished in 21, I think, on structural mechanics, on plate and shell formulations, mainly from the mathematical point. So he's in particular got very interested to matrix and bending and curvature. So now he's a big expert in curvature. But this time he's talking about material he has mainly developed during PhD on doing this, starting with the plates, with the simple stuff, and going to very advanced shell elements.
Thank you.
And Michael is now on his postdoc time in Scotland with Jay, and got recently a Schrödinger project.
Yeah, thank you very much for the introduction, Joachim. Yeah, so we already had a great talk about solids, and now I'm going a bit about the structures, so beams, plates, and especially shells. So shells are also called the prima donna of structures, because on the one hand, if you properly design them, the ratio between stiffness and weight is more or less optimal, so they can carry a lot of loads. But if you do not perfectly, then it's easily that they get unstable. And also in numerical methods, there are a lot of problems like locking. We won't have complicated geometries. We want to have triangular elements, and there are boundary layers. So a lot of things which can go wrong. We also want to have nonlinear. We want to have kinks. And so as an example, we have we can generate now very nice shell geometries, also an open cascade, thanks to Sebastian Hinschel. So for example, we have here a lot of wires, so start building something like this. And then from these wires, we just we can connect them to get also some interfaces and glue them together. And we get something close to the Sydney Opera Hall in this case, a nice shell. And we only fix it here in the pillars, and we just have self-weight. And also, because of all these kinks structures, we also use HP refinement, so we have also some layers. So if we mesh it, make HP refined and curve it, then we get this mesh here, where if we go in, we also have triangular meshes, but also quadrilaterals to resolve probably boundary layers. And we also have, it's a kink structure, so it's not smooth. But we still want to solve a nonlinear Keuter shell, for example, or Kirchhoff-Love shell. So we now also have always the thickness parameter, so because we only have a 2D mesh, but in reality it's three-dimensional. Some material parameters, Savannah-Kirchhoff material law. And we also use some mixed method then for the bending energy. I come to it a little bit later, where we use a similar method like the TNS method. So we also use H-diff-diff element, but it's then called the Helen-Hermann-Johnson elements method. And as we're on the surface, a little bit changes. So we always have like a normal vector on each edge. We have also a tangential and a co-normal vector. And for the membrane energy, for example, we can compute the green strain tensor as we saw before, but now we always restrict everything on the surface. So we have the stretching inside the surface. And so the membrane part looks like this. We have just, again, a variation. So the membrane energy with the green strain tensor, and there's an effect of membrane locking for the experts. So we also use some method to overcome this. I will come to this in a little bit later. And then we also have the bending part, and here again we use a mixed method like we saw now at the end of the talk. I will also come to it. And then we just have like a force on the boundary now, ds, because the shell is a boundary in 3D. And then we can solve the equation, and I also scale the deformation a bit, that we can see the bit that it deforms. So like this part here, the peak goes to the right, but here on the left, and here it heavily deforms. We see here the displacement fields. And we can also have like plot. So the second part was the bending moment tensor, and we see that there's a lot of stress tensor. So there's a lot of stress at this pillar and not so much on this. And if we zoom in, we also see that there are some stresses where we have the kinks, so some kind of layers we have to resolve. So how can we do such objects in NGSolve? And first of all, we can also start just with beams and plates and then create our framework. So the idea of all this beams, plates, shell stuff is that we have a domain where one spatial dimension is much smaller than the others. So instead of trying to resolve the full 3D geometry with tons of elements, which is very inefficient, we say, okay, let's make a model order reduction, so dimensional reduction, sorry, and make only mesh the surface, or for beams, just the beam. And then we also have to derive the equation and hope that it gets much more efficient. And I put here also the derivation for plates, but I won't go into the details because of sake of time. So if we start with linear elasticity in 3D, then, and we have one dimension is very small compared to the others, then we can, for example, do some hypothesis. So saying we have we have some vertical deflection, also some rotation, so a first order shear deformable plate, and also some assumptions on the strains. And then if we do the derivation, mathematics or just computations, then we end with, where is it? Here. This is the Reisner-Minlin plate equation, where we have the first part for beta is the rotation, and so if we have the symmetric gradient of the rotation, this is the bending energy, with some material parameters hidden there. And the second one is the shear energy. So we compare the difference between the gradient of the vertical deflection and the rotations. And the thickness parameter here, they are scaled differently, and this is a source of locking problem if the thickness comes very small. And we can handle, of course, a lot of different boundary conditions, clamped, free, simply supported. And yeah, so this is the Reisner-Minion plate equation. We will look at it. And of course, one is interested if the thickness goes formally to 0, then we get another kind of plate model, which is the Kirchhoff-Love plate. So here we force that the rotations are really exactly the gradient of the displacement field. So in the first figure here, we have the plate, we have the vertical deflection, and then either we have rotation beta extra. This is the Reisner-Minion plate. But if we say this is already given by the vertical deflection, then this is the Kirchhoff-Love plate. So the advantage of the Kirchhoff-Love plate is that there's no locking problem. We eliminated it, so there's no shear energy anymore. But there's no free lunch. We get a fourth order problem. So this is here the Hessian of the vertical deflection, the Hessian of the test function. So we have to deal with this problem instead. But this we can also do. And yeah, also I won't go to the beams, so we can do this dimension reduction also for beams and get the Timoshenko beam or Euler-Bernoulli beam. And if you like, you can go over this notebook here. But I think some beams are nice to play around with locking problems, but not as nice as plates and shells. So I go to the Kirchhoff-Love plate because there we have our favorite method to discretize this. So as I said, this is a fourth order problem. And so in mathematics, we need H2 to have a well-posed problem. So also the derivatives have to be continuous. So we would need C1 conforming finite elements or H2 non-conforming ones, which are not so nice to implement if you want to have unstructured triangular meshes or high order. And therefore, our favorite method to discretize this is the so-called Helen-Hermann-Johnson method, which is a mixed method and also related to the TDNS method. So it's a pretty old method, I would say, with end of the 60s. But then in the 90s, it stopped a bit, and then it regained in the last 10, 15 years more interest again, because now we have nice elements, thanks to Astrid also, and Joachim. So the idea is, again, that we introduce a stress, so a Hellinger-Reisner principle. So we have the sigma, the linearized bending moment tensor, which is like the Hessian of the vertical deflection, and we write it as a mixed formulation. And for the stress, we are again in H diff. And this pairing here is also not in L2 now, but similar like we had for the TDNS thing. So we have it element-wise, plus then we have the jump over the normal derivative for Lagrange finite element, and for H diff we have the normal component is continuous, so we can write it like this. And so let's solve plate problem. So we have a cross geometry here, and we fix it on the top and the bottom, and we apply a force only on the right boundary. And here we have like the formulation for Helen-Hermann-Johnson. So we have H diff H1, and here we have the pairing. So here we have the Helen-Hermann-Johnson pairing. Here we have the force, and we can solve it. Not a big deal. And then we have here, we can see the bending stresses. And here we have the deformation. So we have a strong, so it's this linear problem at this point. So we have a strong deflection here. And then because of the clamped, it starts going to a poor bending here. So here we have, this is just a poor linearized rotation here. And one might say, okay, we have a mixed formulation, which is a saddle point problem. So this normally means that it will get an indefinite system after assembling. So we cannot apply CG or Sparse-Koleski solver, but we can overcome this problem by using static condensation as we know from mixed methods. So we break the normal continuity and reinforce it by a Lagrange multiplier. Can then use static condensation to eliminate the banding stresses on element level. And then if we compare what remains, so we have the vertical deflection and the Lagrange multiplier alpha. And these degrees of freedom are very highly related to the degrees of freedom of the famous Morley triangle, which is used as non-conforming H2 plate bending element. And nothing really changes if you want to use static condensation. You need to make your space discontinuous, have a new Lagrange multiplier to reinforce the lost continuity. And I also write on this line here is for reinforcing the continuity. You say, please use static condensation. And then you can do an harmonic extension. I think there was a tutorial on doing this. Or if you do like Neunteufel, this is also done internally, so I don't go into the details here. And if we do this with lowest order elements, for example, so order 1 displacement, order 0 for the stresses, then we see that the stresses are piecewise constant, and the displacement is, you see it hopefully a little bit, that this is linear. And the Hessian is then, of course, 0. If you compute the Hessian of a linear function, it's 0. But on the other hand, the banding has information about the Hessian of the deflection. So the question is, can we do something better? And for the Helland-Hermann-Johnson method, for example, we also can do a little post-processing to solve local problems to get an improved displacement afterwards. But I won't go into the details here. Just here we see that we can correct it with bubble functions, and then the displacement looks looks better now. It's quadratic. Okay, so there are also other post-processing schemes. But so the Helland-Hermann-Johnson method is very great for solving plate equations for fourth-order problems. It can be done for triangular, quadrilaterals, mixed meshes, high order, low order, very efficient. Okay, and the Reisner-Minion plates, which look like this, as I said before. We have the shear and the bending energy now. And there's the problem of shear locking. So if we don't do something special, if the thickness goes to 0, then the solution won't look good. So I have here a simple example of a Reisner-Minion plate with an exact solution. So we clamp it here on the cylinder, and we see we have a force, and it gets blown up a bit. And the first thing one might think of is, yeah, let's discretize it just with Lagrangian elements. Just Lagrangian 1, for example, for the displacement and the rotation. And here again is the equation, and we have a bending part. We just can write it symbolically what's written there. The shearing part is here. We now know how to do this. And now I make a little test. So if I have here a different sequence of thicknesses, so moderate from 1 to 10 to the power minus 3, and I use polynomial order 2 and a sequence of meshes and compute the error. And if I do it like this, and I look at the relative error, then I see if the thickness is 1, then I see nice convergence. But if the thickness goes smaller and smaller, then we see that the pre-asymptotic regime starts generating, which is called locking. So it wants to be 0 at the beginning. And this is not so nice. And our favorite method for solving Reisner-Minion plates or shells is the TDNS method, adapted to this case, because we want to have that the rotations are in H-curl, in Nedelec elements, because then they fit perfectly to gradients from the de Rham complex, for example. But then we have the problem that if beta is only in H-curl, then the gradient is not well defined. But here we use the TDNS idea to introduce also the bending stress and get the TDNS pairing here. for the bending. And so we will write the bending part. So if you look to the TDNS part, it's exactly the same, more or less. And then we have the shearing energy. Here nothing changes. And now if we look at the same thing, but now I only use linear elements, so we would expect much more locking. Then now we see it's more or less uniform convergence, so no locking at all. So this is a great method for this. Okay, and to shells. So I won't derive the shell equations now, but I want to motivate a little bit the energy. So you already saw I talked about membrane energy, bending energy, shearing energy. And these are in fact the three terms of energies we would like to have to discretize shells. And the notation is more or less the same as in elasticity, just most things are now on the surface. So the green strain tensor we can compute on the surface, for example. And this exactly gives us the membrane energy. So the green strain tensor restricted on the surface tells us how much we stretched the surface. So this is the membrane energy with some material parameters. And so we can, for example, here's just an example where we stretch a plate, and then we can look at the XX component of the green strain tensor. So this is not a 2D mesh, it's a 3D plate mesh, very simple in this case. And the second important energy is the bending energy, which one can motivate by the curvature. So if your geometry bends, then the deformed configuration is now a curved surface. So one needs to understand a little bit about differential geometry and curvature. So if we have a surface like this, and we have the normal vector, then we see the normal vector changes if the surface is curved. So if you compute the gradient of the surface gradient of the normal vector, then we get the curvature information. So this is then also called the Weingarten tensor, or shape operator, or also second fundamental form if you write it in the correct way. And so on Wednesday, I think I will talk more about curvatures. So I don't go too much into details, but we can have now nice tools to compute curvatures on different geometries. So for example, if I have a cylinder here, then I know that the mean curvature is 1 over 2 times the radius, and the Gaussian curvature is 0. So the Gaussian curvature is if we multiply the two eigenvalues of the Weingarten tensor, and the mean curvature is the trace of the Weingarten tensor, so the sum of the eigenvalues. And for a sphere, for example, then we have that the mean curvature is 1 over the radius, and the Gaussian curvature is 1 over radius squared. And so it motivates to define the bending energy as the difference of the curvatures of our initial configuration and the pulled back Weingarten tensor from the deformed configuration. And we can do some algebra and find that the most part is like a Hessian of the displacement, gives us the bending part. And here I just have also a very simple explicit deformation. So here the deformation is chosen that we have a perfect roll-up of our plate. So the bending energy, the membrane energy is 0 because it's a perfect bending. But if you compute the bending energy according to the formula from above, so we can now really implement this formula. We have a Hessian operator on the boundary. We see that in this case it's exactly 1. And the last energy I mentioned is the shearing energy. So here we look if the normals still are perpendicular to the deformed surface. If not, then this is called shearing. We have some shearing energy. So if we have this is the exact normal of the deformed configuration, then we have some shearing here, and we get the new director. And so the nonlinear shearing energy here measures how strong we deviate from being perpendicular to the deformed surface. And so the full nonlinear NUCTI shell, or Reissner-Mindlin shell, consists of these three energies: membrane, bending, shearing energy. We can write like this. And then again we can eliminate shear, assuming that the deformed normals are always perpendicular. And then we eliminate the shear and also the shearing are known, and we get the 3 parameter Keuter or Kirchhoff-Love shell, where we have only bending and membrane energy. And of course we can also now linearize these nonlinear equations to get the linear Kirchhoff-Love and Reissner-Mindlin shell equation. I don't go into the linearization procedure. And if we have, like, the initial configuration is a plate, then in the linear case we again will obtain our Kirchhoff-Love plate and the Reissner-Mindlin plate. And I think because of time I won't go to the linear, but I directly go to the nonlinear shells to show you also some nice shells. Okay, one thing I didn't mention so far in the Keuter shell case especially is that it's not easy to have triangular affine geometry, because for the bending energy we have the derivative of the normal vector, but the normal vector on an affine triangulation is constant. So if we differentiate it, it's 0. And so the whole bending energy sits only on the jump of the normal vector on the edges. And so together with the classical bending energy, we also incorporate the jump of the angles of the normal vectors. And again, you recognize here we use a mixed method with our H-diff-diff, Helen-Hermann-Johnson elements, which perfectly fits here. So we also incorporate the change of the angles. And with this, we can now use the Keuter shell with linear triangulations. We also can have kinked structures with this trick, and also branched shell structures. So this is a very nice trick to write it as a mixed method. So this is then the Neunteufel formulation, membrane energy, and this is the bending energy. Here's the Hessian hidden. But let's look at some examples. So,
I want to ask questions.
Yes?
This jump between the angles?
Yes?
So it's between the normal, between left and right?
Yes.
What is the head here?
Head means on the reference configuration.
Ah.
So I have to compare if my initial configuration already has kinks or is not a plate, then they already have some curvature which sits also in the jump.
Okay.
And so always have to compare the initial and the deformed configuration. I know a lot of notation needed here. But here I use like a cylinder and I clamp it, and so I also use HP refinement, so we can also compare unstructured triangular meshes with quadrilaterals. And I define my normal vectors, the membrane, the Cauchy-Green strain tensor, and I also need to know how the deformed normals change to measure the deformed curvature. And I don't think I go into the details, so I tried to have everything here if you go over it. But if I look now on the energy, so the interesting thing is, so the membrane energy looks like this. And as I said, there's some kind of membrane locking problem if you don't do something, and we use some special interpolation operator into some nice also tensor-valid elements to get rid of membrane locking, so the methods are really membrane locking free. In the bending energy, we have the change of the curvature, change of curvature, that's right, on the boundary, and this is for the normal vectors. And now if we look at this, so here we have the final, after Newton, we have the final displacement, so it's a pretty huge deformation. And here we have also a video how it gets deformed. And yeah, so again, we can use hybridization. So we can get a positive definite system, except from bifurcation points, of course. And another nice example is a cantilever with bending moments. so we can also apply moments without problems. And I just show you how it looks like, because the method is more or less the same. So we start with a bending moment and clamped on the left, and after some time, if chosen correctly, then we get a full circle. And of course, depending on, so normally we would stop here because it would get unphysical if we increase it more, but we can see how far we can go and do more load steps. This is just that it's good with the exact solution. We can do another round of load steps, and then we get it's doubled around. And in this configuration we cannot do more because we have a triangular mesh and it's very coarse, so in the third round Newton would not converge. But if you try it with a finer mesh or quadrilateral mesh, then you can do pretty a lot of rounds, about 7 I could do. Yeah, and also then this was for the Keuter shell. For NACD shells we use like an TDNS approach, so we add the shearing degrees of freedom with the Nedelec elements. But don't go too much into details here. Just I want to convince you that we can also handle structures with kinks and branched shells. So we have here a T structure, which is clamped at the bottom, and we have a shear energy, shear force on the left, such that it should rotate a lot. And we don't need to change our method to handle such branched shells. So some have problems resolving that there's a 90-degree angle after deformation. We only need to use hybridization, but we always want to use this. And I also go to the video, I guess. So yeah, so we see here we have a very huge shear force in this direction, and it rotates about 90 degrees. And we see that if we would zoom in, that the angle is still about 90 degrees. And also, if I look at the banding stresses, then we see that the whole banding stresses are only at the left branch. The right branch undergoes a poor rotation, which makes physically sense. So all the banding induced here goes, the stresses go to the clamp boundary. Okay. And I think we are almost at the end of the time, if I'm
10 minutes.
10 minutes. Astrid, do you want to go to the piezoelastic thing, or make a little switch?
Notebooks from your backup from the.
So I want to say something about the shells too.
Okay, you can
Because
also go.
So just from an engineering point of view, those shells are really unbelievable. When I saw them first, like Michael in Linz, he showed us this example with rolling up the beam, and it was like going, I think, 7 rounds with 10 elements, and that's not standard. Also, I don't know how many shell elements you know that work on triangles and quadrilaterals in the same mesh at arbitrary order and at perfect accuracy. And so I think, so what is the nice thing we have in the shell elements? So when you design a shell formulation, you always talk about curvatures and membrane strains, as we heard from Michael. And in these formulations, we have curvatures and membrane strains as degrees of freedom if we want them. All we need to do is add the additional overhead, let's say, to make things compatible. We add bending moments to have the kinks in the surface due to the nodal H1 elements. We add bending moments which make the kink a continuous transit from element to element. Like you would if you had a hinge. We teach our first semester students, we add a bending moment to control the evolution of the kink in the hinge, and that's the same we do here, what Michael has done in this code. And so the C++ behind the code is highest level, so that's nothing I could do for myself. But setting up a shell problem, if once you have that code, is rather easy, because you read a shell formulation somewhere, you talk to someone about shells, you will talk about energies, essentially. You would talk about curvatures, about membrane strains, about moments, and all you have to do is like copy Michael's code and then extend his exchange the energies he put there, where he chose usually quadratic ones, by the more fancy ones you heard about, like we did it last year, introducing a dielectric shell element or whatever. Do what you want, add degrees of freedom as you want, and then just say Neunteufel converge. It's great. So what we did in this example, so that's a toroidal shell. It's like fixed at this boundary here below and loaded under its own weight, where the load factor, so the G gravity goes up from 0 to 50 to get some exciting things to happen. And what will happen, so here it's fixed, and at some point it will buckle. Yeah, so you will get the evolution of some point somewhere around here where you get almost a kink in this shell. And it's really hard to solve such a problem because you don't know where you will have this almost singularity as the load increases. And what we did is set up the problem. So that's essentially Michael's code. What I need to change if I do some more fancy shell formulation is talk about these first two lines here. That's where we have the curvatures and the membrane strains. The rest is the add-ons we always need. You just take that, copy-paste. And then we do some load stepping. And at some point, when the buckling point is met, your Newton method will not converge. So that's when we did that on this mesh, that's about as far as we got. I think the deformation is added. Where do I see that? I don't know. But here with drawing, yeah, there's a deformation. So you don't see any deformation, you just see around here there will be a problem. Then we do adaptive mesh refinement, also something we can do easily in NGSolve. We just use a Zienkiewicz 2-type error estimate, get the bending moments we have already computed continuous, see where the error is the highest and refine there, and we do that in several steps. We get some refinement here where the problem seems to happen. Another refinement step, and each time, so now the load factor went up to G equals 8, G equals 10.9. We want to go up to 50. Here we have already some rather fine mesh. And then at some point, the mesh was fine enough to get to the final solution with the almost kink here. And another round of adaptive mesh refinement would lead to some additional elements here and probably a more accurate solution. So here you see the evolution of the, I think this point here at the end of the beam with mesh refinements. And that the last one, 10,000 degrees of freedom, is not a lot for such a problem, is then the correct behavior. Okay, coffee break or?
May I ask about 1 minute of Morse 7 dynamics?
Yeah, we forgot about that. Yeah.
One minute. So this also.
Okay, so we had mostly now static or load steps, so pseudo time steps one can say, but also we can do elastodynamics with, for example, a Newmark scheme, a simple one, so we can approximate the displacement and velocity by acceleration and solve the equation. And I think a similar tutorial was yesterday. So we can simply add our update scheme and add it to our formulation. So we have the energy and the update scheme. And then we make a simple time loop. And each time we solve our problem, and then we update the velocity and acceleration. And a simple Newmark looks pretty good. So we have just the volume force, and it bounces down and up. But the Newmark, which is for linear elasticity, very stable, so it's energy preserving. But for a long-term behavior, it might get unstable. So here we have a rotor example with a pretty moderate time step. And I'll just show you how it looks like. So we apply an axisymmetric acceleration at the beginning, and it also gets a bit of stretching. And then after some time, there are higher frequency modes start popping up, which are not good resolved, and then Newton does not converge. So at the last step before the Newton doesn't converge, the displacement doesn't look good, and also the velocity seems to have some higher order modes. So one idea to solve this problem is to use some kind of a damping, but we only want to damp the high frequencies to not damp the whole system. And therefore there's like the generous alpha scheme is very nice, which is like an extension of the Newmark scheme. So we now solve the equation at some slightly different time steps, and also our update scheme has some more parameters, alpha, so just alpha scheme, beta and gamma. But the good thing is that all these parameters depend only on one, rho infinity. If we set rho infinity to 1, then we have the Newmark, no damping. But if we set it like 0.8 or something, then we damp only high frequencies. And the update scheme is also not complicated, so you just write it down on paper, and then more or less you have all the parameters, and then you define again your equation. I also have here, if you want to compute the kinetic or potential energy, this you can also do easily. And then I solve it with rho equals 0.8. And then we see here the results. I put it till 50 or something time end, and it just stays stable. And if we look the energy, then we see at the beginning we increase because we accelerated, and then it's slightly oscillating, but it's stable. So at the beginning it goes slightly down, but then stops. And also if you have stronger damping at the beginning, it will go more down, but also then will stabilize at some point. So we also can solve nonlinear elastodynamic problems easily in NGSolve. Good.